Students, welcome to class 11 physics class. In last class, we studied about the potential energy, gravitational potential energy, conservative force and its properties, and non-conservative force and its properties. Today we discuss the conservation of mechanical energy in case of a freely falling body. We know that freely falling body means when a body falls freely under the action of gravity, it's called freely falling body, free fall of the body. So due to this free fall of the body, the mechanical energy in each case means here we consider three cases. In each case that mechanical energy is conserved. So mechanical energy means kinetic energy plus potential energy. These things we also prove in class 10. So class 10 or 9 I think so. So in 11 we prove this one. So in this figure you see that A, B, C are three positions of the body. At height h, that means at point A, the object is situated where its velocity will be 0. So from point A, the body falls and its kinetic energy increases at the expense of potential energy. So first of all, we calculate the mechanical energy at point A, then at point B, then at point C, and we see that in each point the total mechanical energy expression will be same. So if it will be same, that means it will conserve. So at point A, the object or the body will be at rest. That means no motion is there, kinetic energy is 0. So potential energy is maximum. So potential energy expression U equals to m into G into H. Here we denoted by Ka and Ua because at point A we calculate potential energy and kinetic energy. So here, from here we get both expression as well kinetic energy as well as the potential energy. So the total mechanical energy E equals to K plus U, that is 0 plus mgh equals to mgh. It is the total mechanical energy in case of A. Now we calculate the total mechanical energy at point B. So at point B, at a distance x from A and h minus x from C. So the body falls freely under the action of gravity through the height x, and suppose at point B its velocity is v. So if we use the third equation of motion, v square minus u square equals to 2gs or 2as, so we can write u is 0 because no rest position is there, and v square minus 0 square, that is equals to 2 into g into, because here acceleration due to gravity acts, so 2 into g into x, distance is x. So from that we find out the value of v square. So kinetic energy at point B, half mv square. So in place of v square, if we put this value, so we get mgx. And if we find out the potential energy with respect to point C, so that is mg into h minus x. So if we find out the total energy, that is mgx plus mgh minus x, if you solve these things, you get mgh. So at point A also we get mgh, at point B we also get the mgh. Now at point C, the body finally reaches the ground with velocity v dash. Okay, so here also u equals to 0, v dash square equals to 2 into g into h from third equation of motion. So if we find out the potential energy, that is half mv dash square, if we put the value of v dash square, we get mgh. And when the body finally reaches at point C, the potential energy will be 0. Okay, kinetic energy is maximum but potential energy is 0. So u equals to 0. So E equals to mgh plus 0, that is equals to mgh. So we see that in 3 point each case, the total mechanical energy for freely falling body will be conserved. And if we plot the graph energy versus height, both energy, potential energy and the kinetic energy. So we see that as the body falls freely under the action of gravity, potential energy decreases. At first, at point A, potential energy is maximum, then it will be decreased by h minus x, then it will be 0. But the kinetic energy increases. Here it will be 0, then we get some value, then we get the maximum value of kinetic energy at point C. So potential energy decreases and kinetic energy increases, and this increase and decrease by will be equal. So we can say that the mechanical energy remain constant at all points. And if we plot the graph, so we get this type of figure. Kinetic energy downwards, potential energy this side, and the parallel x-axis, this will be total energy. Variation of so this figure shows the variation of kinetic energy and potential energy and constancy of total energy with height. Okay, now we discuss potential energy of spring. Potential energy of spring, this is a very important things. And the elastic force, this elasticity we also studied in the second part chapter, mechanical properties of solid. In that part we discuss about the elasticity, elastic limit, Hooke's law. So elasticity is the property of a solid object. What is that property? If we remove the force, applied force, the object will return back to its initial condition. That property of an object is called elasticity. That rubber, if we increase little bit amount and if we remove it, it will again return back to its initial configuration. That is called elasticity. But that increment of that rubber, it has some limit. Up to that limit, if we increase and if we remove that force, then it will be returned back, otherwise not. That limit is called elastic limit. Beyond the elastic limit, the elasticity will be lost. So here we discuss the potential energy of the spring. So here three figures are there. First figure, this is a normal position. A block is attached with a force, so no force, extra force is applied over here. So applied force is 0, position x equals to 0, that is called equilibrium position. In second figure, we stretch the spring, and in third figure we compress the spring. By pulling or pushing the block, we apply a spring force to spring force Fs begins to act in the spring towards the equilibrium position. In second figure, if we apply the Fs, if we stretch the spring with that object, it will displace a certain distance, that is x. X is positive direction towards the right side, so x is positive. But a restoring force will apply in the opposite direction of the applied force, due to what, that the object will be returned back to its original position. That is called restoring force, which is restored the object in its equilibrium position. That Fs will be act opposite direction of the applied force towards the right side, that means positive x-axis. But the restoring force will try to return back its original position. That force is called restoring force. So restoring force always acts opposite to the applied force. In third figure, you see that when it will be compressed, so here we apply the force in the negative x-axis, x is negative, but the restoring force is applied right side. Restoring force this time will be positive. Okay, so we can say that wherever the displacement, the restoring force is opposite direction, or you can say that a restoring force is opposite to the applied force. Okay, so according to Hooke's law, the spring force Fs is proportional to the displacement of the block. If we increase the displacement, the restoring force inside the block also be increases. Okay, so Fs proportional to x, so Fs equals to k into x. This k is called spring constant and its SI unit is Newton per meter. Okay, so if we find out the work done by the spring force, so by a small displacement dx, so dw equals to f into dx, that is minus dx means that k into x. Okay, now if we find out the total work done from its initial position xi to final position xf, we integrate this one, so we get w equals to half x k f square minus half k xf square minus half k xi square minus half k xf square. Okay, and if the block pulled from xi and allowed to return back xf and allowed to return back to xi, then work done is 0. Again we pull, and if we remove the object, or if we remove the applied force, then it will again return back to its original position, so we can say that in that time work done will be 0. Clear? Okay. Now conservation of energy in an elastic spring. So in this elasticity, you can think that the energy will be not conserved, but in each and every point, every position, the energy will be conserved. At the extreme position, where x equals to plus minus xm, either it will be positive x-axis or the negative x, and the velocity is 0, k equals to half mv square, that will be 0, u equals to a maximum value half kx square, that is a spring force half kx square. From here you can see that the spring from w equals to, you get half kx square, and this will be stored as a potential energy inside the spring, and so delta u or u equals to half k x square. This is the elastic potential energy of a spring, half k x square. Okay, this is the extreme position. Potential energy will be maximum, kinetic energy 0. At any intermediate position of x, for x between minus xm to plus xm, the energy partly kinetic and partly potential. At any middle point, intermediate means at any middle point, it has little bit amount of kinetic energy as well as the potential energy also. So kinetic energy and potential energy, if you put the values over there, you get the total energy, and you can find out this one. And at the equilibrium position, x equals to 0, so u equals to also you find out, k equals to also you find out the minimum maximum speed. And if you find out the variation of kinetic energy and potential energy, we get this type of graph. In this derivation, if you have any problem, please mention in a comment box, so I will write in a copy this derivation, total energy, how you find out, and I will send it to you in the WhatsApp group. Okay, now next is a power. Define the term power. We also studied these things. Power means work done, rate of doing work done by time. In 1 hour, how much work we can perform, that will be our power. So we can define as rate of doing work, and it is defined it is denoted by P. And power is a scalar quantity because it is a ratio of the two scalar quantities, that is work done and now time. And if we find out the dimension, we get ml square to the power minus 3. And we know that the units of power we use, that is watt. Watt means 1 watt equals to 1 joule per second. And there is also be a bigger unit also with there, kilowatt hour horsepower. Now, main thing here, the new thing that power is a dot product. We already said that the power is a scalar quantity. So scalar quantity, that means it will be a dot product with of force and velocity. How we can find out these things? The work done by a force F by a small displacement dr is given by dw equals to F dot dr. So P means dw by dt. Okay, so F dr by dt, dr means the position with time, that will gives us the v, instantaneous velocity. So P equals to F dot v. So power is an agent at any instant is equal to the product of its force and velocity vector at that instant. Now, kilowatt hour or the BOT unit, Board of Trade unit, it is a commercial unit, and we know that each and everybody's house the meter box is there. It comes as a unit, 1 unit, 2 unit. It has some cost. The meter box also be checked by electric office. Somebody's come and check this amount of unit you used. So per unit has some charges. If we multiply, then that will be your electric bill. And this unit is nothing but it is a kilowatt hour. So the relation between kilowatt hour and joule is 1 kilowatt hour equals to 3.6 into 10 to the power 6 joule. Here two numericals are there. Try to in your home. Solution also be there, and this type of numericals will come in the exam. So if you have any doubt, please write in a comment box that this example or this example you have problems. So I will again solve this in a copy and make one video for that and send it to the group. Thank you very much. Have a nice day.